Hello, 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 hello. Okay.
అప్పుడు వెళ్ళిపోతుంది కూడా వస్తుంది కంట్రోల్ షిఫ్ట్ వెళ్ళి ఏదో ఉంది దీనికి షార్ట్ కట్.
Hello, 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 hello.
Maybe.
That's okay.
Test.
Yes. Yeah.
Yeah, maybe. That.
I will check. How are you?
Okay. Okay. 1, 2, 3. Test. Can you hear me? Can you still hear me? Test. 1, 2, 3. Hello? Can you hear me?
Yeah, I think it's audible.
Sorry?
I guess it is audible.
Yeah.
I could stand at the back and take that.
Okay. So I think the room is okay. That the question is whether that's on YouTube or whatever. Does it work?
Yeah, it's good.
Sunda. Aksar YouTube lo judo.
I think they're even checking the online version of.
Yeah.
Sunda. Done. Oh, 15 seconds late. Yeah.
It's audible in the room and it's audible.
Okay. That's fine.
Yeah.
Thank you.
So any other
Sorry?
is there anything else with the setup? Or is it working fine?
Yeah. It works. Yes.
Okay, cool.
Everything's fine. Okay. Can I take some water from here?
Yeah. You could use these for you as well.
Okay. It's too late. No, I've got the other one.
finishes.
Hi, I'm
Oh,
Prakash.
Hi, I'm Chris.
Very nice thought. I mean, this is something that we worked on and then you have improved on it. I had a look at your paper.
Okay. Thank you.
Very much so.
So I hope that the talk will be nice.
Yeah, it will be difficult to ask questions because you have completed everything.
Yeah.
Yeah.
That's true. So maybe I leave some
Yeah, so
stuff
there was
open.
another thing that was open, but I mean, I think Roland and his student completed it. We had only done it for deterministic well-structured translation system, and then
Yeah. Yeah, you're right. This was recently solved by
Roland and his student.
and yeah. I don't know his name.
Erin Kasky.
Let's.
Yeah, he
I
was my
think we.
student.
Aaron Keskin.
Yeah, he was one of my students when I was postdoc there.
Ah. Okay.
Good. You both should be in the.
Yeah, the same. But we are not suitable to agree with it. No. Yeah, but I'm not good. Onto your laptop, so it's just slick for all of us.
Yes, of course. If we can do this.
Yeah, we've just got both of ours on the memory stick, so.
So I hope it contains no malware. I hope it contains no malware. No viruses.
No. Hey, it's like it might be
Hello.
Yes, this I wanted to ask, so you people have. Oh, good. You have not checked the box.
Yeah, I'm okay.
Okay.
So they've been based on YouTube, right?
Yes, I suppose.
Okay.
So they asked me to get some forms. I do not know.
I'll sign this stuff.
If I can do that
Anytime.
later, right?
Yeah, if you forget, ask me tomorrow, I don't care. So, thank you.
These are your slides.
So you're okay with the talk being recorded and,
Sorry?
you're okay with the talk being recorded and live streamed, right? Okay.
Um,
So you're.
So it goes you,
Yeah,
Rukash,
right.
me.
Get some
But yeah.
time.
Yeah, right. So,
yeah,
You can
Thanks.
also do it after.
Thanks, Chris.
yes, so I hope
yeah, sure, but
weather is also okay.
in case, get three items, let's get this done, right? So I will get a few more.
Can I get your consent?
You're welcome.
What? You want to come in? Where? I see.
But if you are.
You want me to get into where are you based? It's CMI or? Oh, yeah. I mean, I want to visit you. Like all the that's it. I'll make sure I send you. Yeah,
Test. Yeah.
Yeah, so he's been traveling a lot.
Yeah, I just checked that this clock. It's not exactly the same as this on my smartphone.
Mine says, 3.5.
Yeah.
So we are looking at swing content.
Okay. Yes. What kind of swing problem?
So we have, just, we are looking at swing content, subword. They don't have right So I'll just be here in case we have any like.
Yeah. Okay.
Do you help with changing the slides or?
Yes, all of the slides are now on my computer.
Okay, so you can change them with the remote.
Ah, yeah, this also works.
Working.
Yeah.
Good. Maybe this one. Okay, welcome all of you to the next session. This will be the last session and we have 3 talks here. The first talk will be. The first talk will be given by Chris Kosher and it will be on regular separability for VAS.
Okay, thank you. So yeah, topic of my talk is regular separators, or actually the size of regular separators for coverability languages in vector addition systems. Please note that this is a joint work with Georg Zetscher. So what are we doing? So vector addition system, yeah, these are just NFAs with finitely many non-negative counters. They are known to be equivalent to Petri nets and yeah, some other models. And yeah, you can use them, for example, to model behavior of concurrent systems. Then separability or regular separability, yeah, we use this in safety verification. So typically, one has two languages. So one of these languages contains the event sequences that are consistent with the behavior of some system component, and the other language contains the event sequences which are reaching some undesirable state. And yeah, typically, what we want to have is that these two languages are disjoint. And yeah, this is safety verification. And yeah, sometimes we don't want just to know whether they are disjoint. We also want to have some certificate, and these are, in this case, then, for example, regular separators. And yeah, let's see this later. So first, some more formal definition of vector addition systems. So these are quintuples consisting of a finite set of states, some input alphabet. We have some source and target state, and we have a finite set of transitions of the following form. We start in some state P, go to some new state Q by reading some letter from our input alphabet or the epsilon, and we are doing some updates on our counters. And yeah, consider the following example. So what we do here is we start in the source state with all counters are 0. And yeah, we read some A from our input tape and do this update. So we add this vector to our counters. So we are now in this state and our counters have the values 2 and 1. Then we do another transition by reading another A and going back to state S and add 1, 1. Then we go down to this state by reading some B. And now we want to do this transition by reading some A. And yeah, now we cannot increase the second counter anymore because yeah, 3 minus 4 is smaller than 0. So in this case, our transition will fail. Okay, this is the behavior of a vector addition system with state. Okay, there are two possible semantics of accepting words. The first are the so-called reachability languages. These are the sets. Yeah, this is a set of all words, such that if we start in our source configuration, consisting of the source state and 0 vector, by reading this word W, we reach the target configuration, which means we are in the target state T and all counters are 0 again. Unfortunately, this is more or less the reachability problem of vector addition systems, and this is really hard. You will see this in the next talk. So we need some approximation of this, and these are the so-called coverability languages, consisting of all words, such that we start again in our source configuration, read this word W, and end up in some configuration which covers the target configuration. And covering means in this case we are in the target state, but counter values don't matter. It is so yeah. In the counter set there are any non-negative numbers. Okay. Then regular separability. This is the following problem given two languages, K and L, and yeah, we ask whether there's some regular language R such that the language K is contained in R, and it is this L is disjoint from this language R. Note in the general case, regular separability problem is not the same as disjointness. So this means, yeah, if you find some regular separator R, then of course these languages are disjoint, but not necessarily the other direction. However, what you know from Javinsky et al., if you have two vector addition systems, V and W, then their curability languages are regular separable, if and only if the languages are disjoint. And from this, we also obtain that the regular separability problem for VESs is decidable. Okay, for curability languages of VESs. For the reachability languages, it's still an open problem. Yeah, this is something we try to tackle at the moment. Okay. So central question is, yeah, what is the size of such a regular separator of two curability languages, if it exists? What we know is, yeah, that there was some doubly exponential lower bound and some triply exponential upper bound of such a regular separator. But yeah, there's still an exponential gap between these two bounds. And this is what we want to solve here. And we do this with the help of this theorem, which states given two vector addition systems V and W with at most n states and updates of norm at most m. If the curability languages are disjoint, then there's some separating NFA with at most doubly exponential in many states. And this means, in this case, n plus m to the power of 2 to the power of some polynomial in the dimension, or the number of counters in our vector addition systems. And yeah, let's prove this theorem. So in our first step, we want to reduce our problem to the counter instructions. So we introduce some new alphabet, gamma D, consisting of letters AI and AI bar for each counter I, where AI means we increase the counter I by 1, and AI bar means we decrease. And by CD, we denote some new language. This is the language of all counter instruction sequences, such that for each prefix and for each counter, the number of AIs is at least the number of AI bars. Or if you see the yeah, we can see this also as the counter values. So this means the counter value is not negative. Or yeah, let's consider this. So no, we can see CD also as such a diagram, which means for each counter we have such a curse, and all of them are non-negative. Okay. So what we already know is that language L is a vast curability language, if and only if there's some rational transaction T, such that if you apply ZD to this transaction T, then we obtain L. How can we see this? Yeah, if we start in a vector addition system V, yeah, what we do is we just encode these counter updates with the help of our letters. And yeah, for some technical reason, we have to swap the positions. Okay, the other direction is similar, a bit more tricky, but yeah, it's similar. Okay. So yeah. Now we can state if there are if you have two vector addition systems V and W and such a rational transaction T, which describes the semantics of W, then we can separate the probability language of V and W if and only if this strange language here is regularly separable from CD. So what is this strange language? Yeah, we can see this as follows. So this is the set of all counter instruction sequences, not necessarily only the good ones. So we can also have negative counters at this time, such that we give them as an input into W in this case. And this means we just start in our source state, and then we follow the counter instructions on this W, and then we write the letters we've seen on the transitions onto our tape. And in parallel, we read these letters from the tape, and then yeah, we finally have some good run in V. And good means all counters are always non-negative. And this is this strange language here. Well, this was just the first step. Second step, you want to consider so-called basic separators. So for any natural number k, let bk be the following language. This is the language of all counter instruction sequences W, such that there is some counter I, where at some point the number of AIs is probably less than number of AI bars. So the counter falls below 0 at some point. But before we do this the first time, the counter was always below the value k. Or if you consider the following example, so for example, this purple curse here, it falls below 0 at this point, and it never exceeds k before this point. It can exceed this value afterwards, but before it's always below k. In contrast, for example, this orange one does not fall below 0, and the blue one, it falls below 0, but it exceeds k in this time. So yeah, this is language BK. And this language BK is regular. It's accepted by some even small DFA. And small means in this case, it's linear in k to the d. Okay, how can we see this? Consider a DFA for each counter, bki in this case, and this DFA just simulates a bounded counter. And yeah, bounded means in this case bounded by the values from 0 to k. And if we count to k plus 1, then we are in some sync and do not accept. Or if we fall below 0, then we accept and are also in some sync. And finally, BK is just the union of all these languages. Yeah. Okay. So we have these languages BK. And from Jawinski and Zetsche, we know given two vector addition systems V and W, such that the capability languages are disjoint, and yeah, given T be the rational transaction which describes W, then we find some BK, which is a regular separator of this strange language from the slide before, and the language of good instruction counter instruction sequences CD. Okay. So, and this is the reason why we also call these languages BK basic separators, at least for this case. Well, what we now have to do is just to show that this K is always small, and this is our plus step. And here we use some result from Rekov. So let V be some VAS and C be configuration of V, such that if we start in V, we can reach some configuration which covers the target configuration. And in this case, then we find also some short run starting in C and reaching some covering configuration. And short means in this case some W exponential term consisting of, again, the number of states n plus the norm of the counter updates in our vector addition system V to the power of 2 to the power of some polynomial in D. And maybe you can remember that this is already this number from our main theorem. However, it's not exactly the same because yeah, there's some polynomial here. Okay, and what we could finally do is the following. So if V and W are two VASs, such that their capability languages are disjoint, then the strange language and CD can be separated by some BK, where K is in this case this Rekov bound of the product of V and W. And so now we have some regular separator of these two languages. And yeah, we just apply T to these two languages, then we finally obtain a separator of the capability language of V and of W. And so finally, this language is a regular separator, and yeah. Yeah, this finally finishes our proof. Well, so to come to an end, consider the separability problem. First, with the dimension D is part of our input. Then if you want to have some NFA, which is a regular separator of our two VASs, then you obtain a W exponential bound, and especially a tight bound in this case. And if you ask for a DFA, then we obtain some triply exponential bound in this case. And this is done, yeah, just by taking the power set construction in this case. Then you also consider the case where D is some fixed number. And here we have to distinguish some cases. First, whether D is at least 2 or D equals 1. And additionally, we have to distinguish whether we encode our counter updates as unary numbers or in binary. And then we obtain these bounds. All of them are tight. And please note these three bounds here. These three bounds are obtained from these ones just by taking the power set construction. But what is interesting is the case we have just one counter, and our counter updates are encoded in binary. In this case, sorry, then yeah, we can obtain some DFA without this exponential explosion by taking the power set construction. Yeah. Thank you very much.
Yeah, thanks. Are there any questions?
So I remember that in this triple exponential separator, we also used some Rakov. I don't remember exactly how. Could you summarize, like in one or two sentences, briefly, like what's the main trick? Why you jumped from triple exponential to double exponential?
So yeah, so you mean this bound here? So I think the thing was that at some point you did some complementation of the regular separator, and this caused some exponential explosion, and we avoided this by using some DFA at some point here. We said that BK is a DFA. And then, yeah, complementation is easy in this case. And I think that this is the crucial step in this case. That
Yeah, hi. So if I'm just interested in this problem, like I'm given a target and I just want to know whether there exists a word which can, the same reachability and coverability problem, instead I'll just ask like whether there exists a word which can reach this particular target. Are these problems easy to solve or? So I am in, let's say initially P0, and the question is, and I'm given a target. And the question is, does there exist a word which I can read from P0 which reaches the target with, let's say, zero vector and maybe some non-zero vector?
so sorry, I don't get your question.
So the reachability is like from P0, can you reach the target zero vector, right?
Yes.
So if the question is, does there exist a word which does this? Is there a word which I can take from P0 that reaches T0? So is the problem easy to solve, or is it?
So you mean that this one?
Yeah. So
Yeah,
the question is like, is L reach empty? Yeah, you could also.
So this is reachability problem, and this is Ackermann hard.
Okay.
It's even complete. So this is the reason why we are not considering it here, or why we also consider these coverability languages. And coverability is X-based hard. So this is of much.
So even if
better
I want to
complexity.
check whether this L curve is empty, it's
so emptiness is also coverability.
okay. Yeah, thank you.
Yeah, so if there are no other questions, I had one. So you looked at coverability, separating coverability, and you said reachability, I mean, separating reachability, two reachability languages is open. This is what one of your slides said, right?
Yes.
But what if you ask I give you a coverability language and a reachability language, is this immediate or?
Good question. Probably this is also open.
Okay.
I don't know.
Yeah, if there are no more questions, let's thank the speaker. Okay, so the second talk will be given by Lukasz, and he will talk to us about new lower bounds for reachability in vector addition systems.
Okay, hello. My name is Łukasz Orlikowski, and today I would like to present to you a joint work with Wojciech Czerwiński, Ismail Jeker, Sławomir Lasota, and Jérôme Leroux about new lower bounds for reachability in vector addition systems. So what's the presentation plan? First of all, I would like to present history and definition of the problem. Then I will formulate our main result. And at the end, I will show you some of the techniques which allowed us to improve the lower bounds. Okay, so vector addition system with states is a central model in concurrency. You can define it in many equivalent ways, but one way to define it is to equip a finite automata with a storage of non-negative integers of some fixed dimension D, and to equip each transition with an integer vector of the same dimension. And if some transition is fired, then you add a vector on transition to the vector inside this storage. Okay, so actually, we often, instead of working directly with the vector addition systems, we work with counter programs, which can be almost directly translated to vector addition systems. And in the basics setup, each line in this counter program is either some modification of the counters, like the first one or the third one, or the second possibility is that the line is a loop, and that means that you can loop the body of the loop for some number of times. So, for instance, this first line here will be translated to this transition from S to P1. And the loop in the lines second and third will be the loop from P1 to P1. And if we have two consecutive loops in the counter program, we can translate it in the VAS by adding transition between two states with no effect on the counters. Okay, so actually, we can extend vector addition systems in many ways to get some more powerful models. And one way to extend this is to extend VAS with a stack and some finite alphabet of stack symbols. And then you, on the transition, you can have modification of the counters as in the standard VAS, and also some operation on the stack, like pushing some symbol on the stack or popping some symbol from the stack. And if you have this pop command, you can only fire this transition only if this symbol is on the top of the stack. Okay, so what is actually the reachability problem for vector addition system with states? So you are given a vector addition system and two of its configurations. So you are given a tuple in which you have some state of the VAS and also some values of the counters. And the question is there a run from the starting configuration to the final configuration? So for instance, you can ask in this vase here, can I go from P110 to Q210? And in the case of a push-down vector addition system, in the configuration, you also have like the state of the stack. So what is on the stack? Okay, so here is example of run in vector addition system. So from P102, you go to P201 by firing firstly this loop from P to P, then going from P to Q by this transition with no effect on the counters. Then you fire a loop from Q to Q, and then you go back to P by this upper transition. So, okay, so now I will define a family of fast-growing functions from which you can get a complexity classes. And yeah, so f1 of n will be defined as 2 times n. F2 of n will be defined as 2 to the power of n minus 1. And in general, fd of n will be defined as you compose n minus 1 times fd minus 1, starting from 1. So if you look at this definition, you can think of f3 of n like something like tower. It's not exactly tower, but approximately you can think of this like of f3 like this. And also fn of n will be kind of Ackermann. Okay, so what's actually the history of the problem? So in 1976, Lipton showed express hardness of the reachability, and for many years it was actually the best known lower bound, and many people thought that the whole problem is express complete. So decidability was shown by Mai in 1981. And some simplification were made by Kosaraju and Lambert. And the first upper bound was presented in 2015 by Leroux and Schmitz. That was cubic Ackermann upper bound. So as you can see, there was a huge gap between this upper bound and the best lower bound back then. And in 2019, Leroux and Schmitz improved their upper bound to be Ackermann upper bound. And also in 2019, Czerwiński, Lasota, Lazic, Leroux, and Mazowiecki have shown tower hardness. And this was a really big breakthrough because it was like the first lower bound since the Lipton's one. So yeah, but still the gap was quite huge. And finally, the gap was closed in 2021 by 2 independent proofs, one by Jérôme Leroux and the second one by Wojtek Czerwiński and me. So Jérôme has shown FD hardness in dimension 4D plus 5, and we have shown FD hardness in dimension 6D. So we know that the problem in a fixed dimension is in FD plus 4. So these results created a big gap. If you look, they closed like the gap in general, but they created a gap in a fixed dimensions. So these results were followed up by approved by Sławek Lasota and he has shown FD hardness in dimension 3D plus 2. And I believe that this is actually the most simplest proof if you want to look why the whole problem is Ackermann complete, Ackermann hard, and Ackermann completeness is from the Leroux and Schmidt's upper bound. And as for the pushdown, even decidability is not known. And all the lower bounds up to now were like directly inherited from vector addition systems by just treating them as a pushdown. So what is our contribution? Our first theorem is that the reachability problem for vector addition systems is FD hard in dimension 2D plus 3. So this doesn't close the gap fully, but make it smaller. And the second theorem is that the reachability problem for pushdown vector addition systems is FD hard in dimension D half plus 6. And this is, I think, interesting because you cannot have such a result for normal VASes. So in some sense, this shows that pushdown vector addition systems are indeed harder than just vector addition systems. Yeah, and this is like the first lower bound, not inherited directly from VAS. Okay, so what are the techniques? So yeah, let's first define Minsky machine. So this is a counter program with 0 tests and 2 counters. So you have 2 counters, like in a VAS, but you have also ability to test some counters for 0. So you can fire some transitions only if a specific counter is 0 at that moment. And a reachability problem for this machine is in general understandable because you can like quite easily simulate Turing machine. And but some versions of the problem are decidable. So in particular, FD0 test reachability problem is FD hard. And so in this problem, you are given a Minsky machine and 2 of its configurations, S and T. And the question is there a run from the starting configuration to the final one, which does exactly FD of size 0 tests? So that's actually the problem from which we reduce. And yeah, so as you can see, because like this Minsky machine has 0 tests and VAS has not, we have to be able, in some sense, have some technique which will allow us for simulating some 0 tests. We can not simulate infinite number of 0 tests, but we can like try to simulate some bounded number of 0 tests. So the technique which was used in all previous results was multiplication triple technique. And it's as follows. So let's have a triple B with B to C and 2BC. And this will allow us for C0 tests on B-bounded counters. So how can it be done? So first, let's introduce a macro, flash X, Y, Z. And this is a simple loop which decrease X and Z and increase Y by 1. Okay, so we have such a triple. And we want to simulate a zero test on X. So the test will look as so. So first we will do a flash BXZ, and then we will do flash XBZ, and then we will decrease Y by 2. And why does it work? Because like in the whole program, we keep two invariants. The first invariant is that the sum of the sum B plus X is constant, it is equal to the big B value. And the second invariant, which we want to keep, if all the zero tests were simulated correctly, that B plus X times Y is equal to Z. So let's see that these zero tests, like it does not change the sum B plus X, because like this flash is -1 on B and +1 on X, and the second one is -1 on X and +1 on B, and Y is decreased by 2. So the left-hand side is decreased in total by 2 times big B. And what is with this Z? So so the Z is decreased as the same amount as how many times a loop inside this flash plus how many times a loop inside this flash. Like these loops were executed. So as you can see, because B plus X is equal to big B, the total number of loop execution can be 2 times big B only if X was 0 at the beginning, because this loop has, like loop inside this flash has to be fired B times, and also in the second one. Okay, and the triple tech, we actually in the paper created a new multiplication triples technique, which allowed us to go from 3D plus constant to 2D plus constant, and it looks a bit differently. So the triple will look like, will look like A, B, and the third counter will be 4 to the power of B minus 1 times A. And this will allow us for B0 tests on A-bounded counters. So this triple is much more technical, I think. And I don't want to go in deep details, but yeah. So by one also, sorry. Yeah. And the invariant which we keep, we want to keep the invariant that A plus X plus Y plus T times 4 to the power of B minus 1 equals C through the whole program. And yeah, we want to keep this invariant only if X was indeed 0. So you can look at this invariant a bit differently. So that the sum A plus X plus Y plus T times 4 to the power of B equals C plus A plus X plus Y plus T. So during the program, we want to keep the sum on the right-hand side constant. So if you decrease in the zero test b by 1, this sum has to be multiplied by 4. So so x, we want to test x for 0, and we assume that at the beginning of this program t is also 0, and we will, like, if x will be 0, we will leave it 0 also at the end. So in fact, you want to, so what this program does, it actually multiplies a and y by 4, and keep this sum constant. Okay, so actually to show hardness, the main challenge is producing such triples, because if we would have a big triple, then we will be able to simulate a Minsky machine for like FD zero test steps. So this can be done by producing bigger triples from smaller ones. So in fact, we can produce triple m fd of m 4 to the power of fd of m minus 1 times m by using 2d plus 4 counters in case of VAS, and d half plus 4 in case of pushdown vector addition systems. Yeah. So how actually buses which produce such triple look like? I don't want to go in deep technical details, but the main thing is that you have d-nested levels of counters. And on each level you have B and C. So the second counter from the triple and the third one. And like this new triple technique allowed us for having one common A for all levels. So yeah. So we can have on each level 2 counters and one common A for all of them. So if you would look closer into these programs, you will see that B counters have stack structure. And therefore, we were able to put all of these counters to the stack. If you look further, if you look closer, then you can see that half of these C counters, like if you look on the odd ones, you will see a stack structure here. If you look on the even ones, you will also see a stack structure. So that means that also half of the C counters can be put into the stack. So yeah, so actually what we did is we took VAS producing these big triples, and we put all of the B counters onto the stack and half of the C ones, and because of that we got D half. Yeah. Yeah. So that's all from me. Thank you.
Yeah. Are there any questions?
Yeah, so sorry, this is not very related to push down, but to stacks. But I wanted to know that what you said was that this is the first result which is just related to stack and not inheriting the results from VASs. An interesting situation is branching vector addition systems because the upper bound is not even known. And also in that case, the best lower bounds are also inherited from FAS. So do you think you can do this multiplication triple technique there?
So yeah, so like for push down, the upper bound is also not known, even the decidability, and I think like this is the case also for branching. So we were looking for some time on the branching, and it was like quite hard to improve to use this multiplication triples there in some other way than just doing a standard pass.
Are there any other questions?
Like I'm pretty new to the field, but like how in automata theory we have like something in our intermediate model, right? Like deterministic push-down automatas. They recognize languages like between DFAs and between PDAs. Like that, do you have like some deterministic version for a PVAS?
So I believe like when you ask about only reachability, that doesn't make sense to have something like deterministic. But if you will extend like transitions with letter and ask for languages of determined by reachability condition of some configuration, then probably it makes sense to think also about deterministic ones.
Yeah, so I had a few questions myself. So you seem to use the full power of stack. No? So what if you just have counter?
If you
just have a counter instead of a stack?
Count, yeah. So that's only like a VAS, right? Then
with zero test.
With zero test. Okay, so 1 0 test. So that's known to be decidable.
But lower bound.
But no, I don't. I'm not aware of any lower bounds not inherited from the VAS.
Okay. Okay. Also, I had another question. So you said this push down decidability of push down is not known. But what if you just restrict it to a weaker version of push down, say reversal bounded push down is something?
I don't know actually.
Okay.
Yeah, I don't know.
Yeah, thanks a lot. Let's thank the speaker.
Oh. Hello, is this okay for volume?
Yeah.
Seems all right.
Yeah, so we'll have our last talk of today, and we'll have our last talk of today, and this will be presented by Henry Sinclair Plank, and he will be talking to us about acyclic Petri nets, workflow nets with resets.
Thank you very much, Prakash. Right, yeah. Hello, my name's Henry. I'm a PhD from the University of Warwick, and indeed today I'm going to be talking about acyclic Petri nets and workflow nets with resets added. This is joint work with my supervisor, Dmitry Chistikov, and also Wojciech Jawiński, Piotr Kaufman, and Filip Mazowecki. And don't worry if you're new. I get the impression that some people are not so familiar with VAS or Petri nets. I'll kind of give a definition, but it will be fairly light touch for those that do know. So yeah, without further ado, what's a Petri net? So we've already heard in Chris's talk that Petri nets are equivalent to VAS, but they look rather different. This is a Petri net. Here's an example. So Petri nets have places and transitions that can move tokens. You've got a non-negative number of tokens in each place. Here I've got 4 tokens in P1, 5 tokens in P2, and then in Q, R1, and R2, I've got 0 tokens. And transitions can move them around in the way that you would expect. So if I was to fire T1 here, I would consume 1 token from P1, 1 token from P2, and then I'd put 3 into Q, like this. And then now I have the ability to fire T2 because I've got 3 tokens in Q. I can take 1 to consume. I can put 5 in R1 and 1 in R2. Okay, fine. And this is equivalent to VAS. I won't explain why. If you want, I can explain separately afterwards. That's fine. I'll introduce a little bit of notation that's like slightly different. So a marking is just a configuration. It just tells you how many tokens are in each place. In this, I've got 3 in P1, 4 in P2, 2 in Q, 5 in R1, and 1 in R2. And a run is the same kind of thing for VAS. It's just a firing sequence of transitions. You've seen one already. I've just shown you a very short 2-transition run where I started with the marking 45000, and I went to this marking here by first firing T1 and then firing T2. And you've already seen now twice, now for the 3rd time, some decision problems for these models. So I'm going to have 2 decision problems that happen to be reachability and coverability. Who would have guessed? They take input a Petri net in this case, an initial marking I'm going to call U, and a target marking I'm going to call V. Reachability says I would like to go from U exactly to V, and coverability says I'd like to go from U to some marking that is at least the target. So I'm allowed more tokens in each place than necessary. Workflow nets is something else we study. So in workflow nets, they have some special features. This is not a workflow net, and I'll explain why in just a moment. In a workflow net, you have some designated initial place, we'll call it I, and some designated final place, which will denote F. I cannot be produced to, so it can only really be consumed from, and F has the opposite, that it can be produced to, but cannot be consumed from. And every place and every transition is on some path from the initial to the final. Now, this is not a workflow net, firstly, because I've not given you the initial or final place, but also even if I did, let's say P1 is the initial and R1 is the final, then P2 is not on a path between the initial and the final. So I need to change this. I'll add an initial place, and I'll add this transition to produce some tokens to P1 and P2, and I'll add a final place. And now notice that every transition and every place is on some path from the initial to the final. And so, yeah, this indeed satisfies the properties that one needs for a workflow net. Surprisingly, but not surprisingly, if you think about it for a short while, the complexities of reachability and coverability coincide for Petri nets and workflow nets. So we've already heard from Łukasz that reachability is Ackermann complete and coverability is X-space complete. These are, like, to answer the question from the gentleman in the pink shirt earlier, very difficult problems, and they remain difficult even with the restriction of workflow nets. Very roughly speaking, you do roughly what I did here. You take any old Petri net, you add a new initial place, you add a transition like T0 that sort of spawns the initial marking, you add a new final place F, and some like final transition, in this case T3, that kind of consumes the target marking. You have to do a little bit more because you kind of need to make sure that every place and every transition is on some path, but you can add some extra places and transitions to make this work out. But I won't explain anymore. So I'll move on to Petri nets with resets. This is a more powerful model. So when I add resets, I'll denote this with this red dashed edge. So in this case, transition T2, when fired, resets P1 and R2. What does that mean? So the semantics are as follows. First, a transition consumes, then it will reset, and then it will produce. So to have a look, what happens when you fire T2 from this marking? First, you consume 1 token from Q, then you'll just empty P1 and R2 to reset them, and then you'll do the production. So I had to expand R1 a little bit to shove 10 tokens in there, and I'll have 1 token back to R2. This problem's really, really hard, right? Like we've jumped up from Ackermann to undecidable, unfortunately, and coverability jumps up from X-space to Ackermann. And so these problems are like seriously difficult. And so if you wanted to do any form of verification, you're probably going to struggle. And like, why resets? Like, why would you want resets? In some systems, either by design or by accident, you might end up in some configuration that's kind of bad in some sense or not useful. You might want to literally restart a process. It's very natural. And you can't do that in a VAS or a Petri net because you don't have 0 tests. You can't kind of come back, test for 0, and then continue. So maybe you just have a button that does reset, and resets indeed model this nicely. But unfortunately, the complexity really jumps. So something's got to give. We add acyclicity, so we restrict the model after extending it, hoping to get some reasonable tractable decision problems. So the semantics don't change. it's just the structure of the Petri net that we consider. That's the only thing that changes. Actually, this thing is acyclic. So in our definition of acyclicity, you just look at the graph consisting of the places and the transitions connected by these consumption and production arcs. We do not count the reset edges. In a sense, it's hard to say which direction they follow. We'll call the productions arcs and the consumptions arcs, but we'll call the resets edges. There's sort of no directionality. It does look like you have a cycle P1, T1, Q, T2 back to P1, but this uses a reset edge, which doesn't count. And so, yeah, this example the whole time, surprisingly, has been an acyclic Petri net with resets. And yeah, this talk is about like what we study. So we study acyclic Petri nets with resets and acyclic workflow nets with resets. And just to give a mention that acyclicity really restricts your model without resets. So if you were just to restrict Petri nets and workflow nets to be acyclic, then reachability and coverability are all NP complete in all the four combinations where you combine reachability and coverability in Petri and workflow nets respectively. So this really restricts the what you can do. So let's talk about like what we've done when we have both the extension with resets and the restriction with acyclicity. So indeed, we study acyclic workflow nets and acyclic Petri nets with the resets, and we indeed study coverability and reachability. So the first theorem that we have is that if you consider workflow nets and the reachability problem, then you're in p-space. This is a massive improvement over what we had before, which was undecidability, but is somehow harder than NP. And this is what one would expect because we have resets. These are quite powerful. And theorem 2 says that if you consider coverability and instead Petri nets, then you remain inside p-space for somewhat similar reasons. And theorem 3 is that actually these problems are pretty tough already. So if you have coverability and the workflow restrictions, then the problems are p-space hard. And so we can do a bit of jiggery pokery and notice that this lower bound extends both ways, right? The reachability problem is harder than coverability, so this lower bound will extend. And well, workflow nets are just a strict restriction of Petri nets, so of course this lower bound will extend downwards. And so we know that coverability in acyclic Petri nets with resets is p-space complete, and reachability in acyclic workflow nets with resets is p-space complete. And the same true in the other direction. So these upper bounds come back for acyclic workflow nets for the coverability problem. And so this problem too is p-space complete. So far, so good. But unfortunately, with acyclicity, undecidability persists, which I think is rather surprising. And this is the first kind of obvious occurrence when the complexity of reachability differs in workflow nets and Petri nets. We saw without resets and without acyclicity, both problems were Ackermann complete. With just resets, it became undecidable in both models. And with just acyclicity, both were in NP, but now we have a difference, p-space to undecidability, which is kind of odd. And I should note, this is important, but will not be focused on in this presentation, that these results hold regardless of the encoding. And when I say encoding, I'm talking about the encoding of the arcs themselves, like how many tokens you're consuming or producing to certain places. If you encode this in unary or binary, p-space holds either way. Okay. So I'll share some of the ideas that we used to get here. So the first is for theorem 1, which is acyclic workflow nets with resets. The reachability problem is in p-space. So, okay, let's suppose reachability holds. Indeed, there'll be some initial marking. We'll suppose this is at this one is like putting one token in the initial place, and we're aiming for reachability where we have one in the final place at the very end. We're going to ignore resets for a moment in the run. I'll explain why in just a moment. And we're going to consider the number of times each transition is fired. Like, why ignore resets? Well, if you just pretend to remove resets from your model, well, then the markings that you see after firing a transition are only going to be bigger because resets only decrease the number of tokens that are available. So if you ignore them, you see bigger markings. I'm going to argue that even once resets are ignored, the markings you see are not so big. And we're going to use the following fact, which is that workflow nets have the property that all transitions must consume a token. Like, why is this the case? Suppose that's not true. Suppose there's a transition that doesn't consume anything. Well, if it doesn't consume anything, then there's no incoming arc. But I said that a workflow net must have every transition has a path, is on a path from the initial to the final. As if there's no incoming arc, then certainly it can't be on a path from the initial to the final. So indeed, we must be consuming something. And so from the very initial place, there will be a transition that consumes a token, right? Like this has to happen. And suppose it produces m many tokens. It doesn't matter exactly what m is, but suppose m is the maximum number of tokens any transition produces. So firing this will shove m tokens to this next place. And well, T1 can only be fired once. That's pretty obvious. And now suppose T2 does the same thing. It consumes just one token because it needs to consume at least one token. And suppose it too produces the maximum number of tokens. This could be fired m many times, right? Because we would have produced m many tokens to that place. You can see this argument repeating, right? And by the nth transition, we'll be able to fire this at most m to the power of n minus 1 many times, right? If you imagine this all stacked up. And if I suppose there were n many transitions, then we have a bound on the maximum number of tokens that were possible to put in a place. This is m to the n. And remember, this is just without resets. If there were resets, this number might be even smaller. So this really is a global bound on the maximum number of tokens you could physically put in a place in a workflow net. And well, this marking can be represented using polynomial many bits. So if you write down a marking in binary, then this will have log of m to the n amount of space required. If you kind of see this out, this is m times log m. N is the number of transitions, is clearly bounded above by the size of the machine, and log m is clearly bounded above by the size of the machine because it's the maximum number that you ever see on top of a production arc, sorry. And so this is a polynomial value. And how do we get the p-space algorithm out of this? Like, what's the kicker? Well, if I can write down any reachable marking using polynomial space, then I just use a non-deterministic polynomial space exploration algorithm over the states or over the configuration space, or rather the marking space, as I would call it. So that gives the rough idea. So the next idea is the p-space lower bound. This is a bit harder, and I think I've got time to explain through some of it, so we'll see how it goes. So we say that coverability, so not reachability as we saw in the previous slide, is p-space hard. So we're going to reduce directly from the quantified satisfiability problem. So let's suppose we're given some quantified satisfiability formula. So the flavor that we care about is when we have universally quantified, then existentially quantified single variables nested n many times. I'm going to, for sake of clarity, I hope it's okay, represent universally quantified variables with y and existentially quantified variables with x. And so we care about this statement here. For all y1, there exists an x1. For all y2, there exists an x2, etc., such that phi holds. Okay. And we're going to construct a net. Here's the sketch. I will show an example, and I'll try and talk through it. So we're going to have some places. These are really representing gadgets. This is not like true to the form, that represent like each quantified variable. And they'll be in some way consumed from and produced to places corresponding to each literal. So if we would like to, if we have, there exists x1, then we'll be able to choose whether we put a token in x1 or x1 bar. And for universally quantified, we'd like to iterate through. So first we'll put a token in, I've made a typo here. These should be y's and x's mixed. But you get the idea that if you have a universally quantified variable, then you would like to copy down a token to first x2 and then x2 bar to go through all the combinations of the universally quantified variables. And then these will be kind of pushed to all the clauses for which those literals belong to in some way. And then finally, we'll have this like special satisfaction transition, which will try and gobble a token from each place. And if you have a token in a clause place, this will be representing that a clause is satisfied. So you'd like to be able to collect tokens from all of them, saying like, oh, all clauses are satisfied, which is what you would like for QSAT. And then we'll put one token in this final place F, right? Remembering this is a workflow net. And the number of tokens in F will count the number of times we satisfy. And we'd like to be able to put 2 to the power of the number of universally quantified variables, many tokens in F, right? That's like how many times you have to check QSAT. Okay, so maybe a bit more detail on how this works. Here's a horrendous example that I made earlier. It's not as bad as it looks. I'll talk you through it very briefly, but I kind of just wanted to show you that firstly, this isn't very easy, and also that it is real. Like there's a reason I gave you a sketch first. We'll have an initial place all the way at the top left and a final place all the way at the bottom right. If you kind of look, Yeah. If you look here, first you'll be producing tokens to not Y1. This is a universally quantified variable. And then there'll be a token sat in this place. And then later you'll be firing a transition into Y1. So at some point there'll be tokens here, and another point there'll be tokens here. However, for existentially quantified variables, you get the choice when there's a token here, whether to fire this transition or this transition. So for universally quantified variables, you're really forced to sequence, setting it to false, then true. Whereas for existential variables, you get to choose whether it's false or true. And this kind of nests itself in some crazy way. These values here are to sort of keep the number of tokens in memory, so to say. So we'll produce more tokens for like outermost quantified variables and less tokens for innermost quantified variables. And note, like, I thought this was about resets. Like, I haven't drawn the resets because it would be an absolute headache if I did. Pretty much every transition resets every single place below it and to the right, which would make a lovely dotted red mess if I were to do so. So then once you have these loaded up with some tokens, you'll then have these transitions that will fire into the clauses. So C1, C2, C3, and C4 correspond to these three clauses. Just to look at C1, for example, you'll be pulling a token from the Y1 place. You'll also be pulling a token from the typoed X1 place, and you'll be pulling a token from the not Y2 place. And there's these extra 6 places that correspond to like dummy clauses that are just Y1 or not Y1, X1 or not X1. They're there just to force you to fire every transition through. And then eventually you'll have a satisfaction transition that will gobble tokens from every place, reset them all, and put 1 in F to say like, yep, we survived this iteration of QSAT. I'm happy to explain this in more detail for those who are interested later, but I'll leave that for now. The final idea that I'll share with you. Yes, question. I've made a mistake. It should be from the X, not the X bar. My apologies. You're right. And to share the final idea, I'll share roughly how undecidability works. So I claim that reachability with acyclicity remains undecidable. How does this work? We do it with 2 lemmas. The first, instead of dealing with resets, as we've seen in previous presentations, we're going to deal with 0 tests because they're ugly. This is a classic reduction using resets to simulate 0 tests, so I won't show it here. The second lemma is the interesting one. Like somehow we can just remove acyclicity. Like what gives? Very roughly, we're going to simulate not necessarily acyclic transitions. We're going to simulate all the transitions with some sort of transition controller. Imagine this is the Petri net, just the most simple cyclic thing I could draw that's remotely interesting. So note that there is clearly a cycle from S to R, down to T, back to Q. Like I'm not going mad. So we're going to draw this thing. It's not actually as complicated as it looks. I'll talk you through it. So we're going to have these top transitions that are going to be guessed. Note that this is not a workflow net. This is a Petri net. So we're allowed transitions that are not reachable from some given initial place. So if you would like to fire S in the original, we're going to fire S prime. It's like you guess the transition that you're going to fire. This would produce 2 tokens, right? 1 to the left and 1 to the right here. This transition below the left place will simulate the consumptions. Note that it consumes from P and consumes from Q, just like S does in the original. And this transition here will simulate the productions. Look, it will put a token to R, just like S puts a token to R in the original. And note that this transition, the like production simulator, requires that this place is empty. So really you have to fire this transition before you fire this transition, which preserves the semantics of Petri nets as one would hope for. And moreover, once you fire S prime, guessing that you're going to fire S, you'll put 2 tokens here. But notice to fire S prime or to fire T prime, you need all of these places to have 0 tokens in them. And so you can only fire them once they're all empty. So you guess S, you put 2 tokens here, you have to fire this transition first, then this transition before you can fire S prime or T prime again to continue. And this thing's always acyclic. Notice that at the very bottom, you'll have the consumption places, and there are no cycles here. Like it looks like you might, but indeed the bottom level of this acyclic Petri net are the consumption places. Then you'll have the places that are like simulating the original places, and then you'll have the production transitions themselves. This thing's acyclic because the 0 tests don't form a cycle as well. And so this gives you very roughly the ability to simulate not necessarily acyclic transitions. And although I've not included it here, you could just have 0 tests in the Petri net, copy them over to here, and now you're simulating just an arbitrary Petri net with 0 tests. And reachability here is undecidable, so reachability with a cyclicity force must also be undecidable. And so that concludes the talk. So to summarize, here are our results. We show that coverability and reachability in a cyclic workflow net with resets are both p-space complete, and a cyclic Petri net with resets, the coverability problem is p-space complete, but the reachability problem, surprisingly and maybe unfortunately, is undecidable. And for future work, this could be a good basis to study the soundness problem, which I won't define for sake of time here, in a cyclic workflow nets with resets. And there is also the question whether reachability or coverability in acyclic affine Petri nets or workflow nets is decidable, where affine is a strengthening where you're able to multiply the number of tokens. So you can take a transition that doubles the tokens from one place to another. So this is a more powerful model, but maybe with acyclicity, this becomes like reasonable. Yeah, thank you very much. I hope you enjoyed my presentation.
Thank you, Henry. Are there questions?
Yeah, so is this problem studied for one-safe Petri nets with resets?
In what, sorry, with resets?
If I consider one-safe Petri nets with resets.
So a cyclic one-safe
Yeah.
Petri nets with resets. Best of my knowledge, it's not been studied.
Okay, thank you.
You're welcome.
Are there other questions?
That much of a difference from what you have told already. Like you have this n to the m-1 upper bound on the total number of tokens. With affine also.
I don't think it would give you, I'm not sure if it would give you a polynomial space upper bound, because in affine, you can have a transition that doubles the tokens of the previous. So if you imagine this, you can then maybe double exponentiate, so maybe it gives you an exponential space upper bound. So yeah, I think an exponential space upper bound might follow immediately. I'm not sure if you get polynomial space, but sure, decidability seems pretty obvious actually. Thank you.
There will be 20 tokens in the next one, or what does it mean?
Yeah, so an affine function is like a linear function, like ax plus b. So if I have like 10 tokens somewhere, I can then fire a transition that produces a times 10 plus b many tokens in the next. So if I have the function 2x plus 0, then indeed that would do the case.
Any other questions? Yeah, if not, let's thank the speaker.
Thank you.